Now, when the algorithm is presented, we need to estimate the running time. For the quicksort algorithm, the running time analysis is a little bit tricky. So before stating and proving the theorem about its running time, let's build our intuition. First of all, let's consider a pathological case when somehow it always happens that we select the minimum value of our current subarray as our pivot element. Well, in this case, let's see what happens. We have a current subarray, say of size n, and we select its minimum value and as a pivot and partition the subarray with respect to this element. Since this is the minimum value, its final position is just the first position in the resulting array, right? Which means that we partition into two parts. The first part is just empty. We have no elements smaller than our pivot. And the second part contains n-1 elements, because all the remaining elements are greater than our current element. Okay, so in this case, and if this happens at each iteration, at each call to partition procedure, then we can write that the running time of our quicksort algorithm satisfies the following relation. T of n is equal to n plus T of n minus 1. The term n here corresponds to the running time of the partition procedure. Well, it is actually big O of n, but just to simplify, let's put n here. Well, let me also recall you that, if we have an array of size n, then the partition procedure indeed works in time big O of n, because it just scans the subarray, right? So now let's see what is the solution for this recurrence relation. Well, we can just unwind this recurrence relation term by term. So we have n plus T of n minus 1. Let's replace T of n minus 1 by n minus 1 plus T of n minus 2. Then we replace T of n minus 2 by n minus 2 plus T of n minus 3. And we keep doing so. So what is left is the following sum, n plus n minus 1 plus n minus 2 and so on. So and we know this sum already. So this is an arithmetic series and we know that it grows quadratically, which gives us something strange. Our quicksort algorithm works in quadratic time, which means that it is not quick actually, right? Well, we will resolve this issue later. Now let's consider a slightly different case. Assume that somehow we always partition into two parts such that one of them has size, for example, n minus 5, and the other one has the size 4. Well, I claim that even in this case, first of all, note that both these cases correspond to very unbalanced partitions. In the first case, we have two parts, one of size 0 and one of size n minus 1. In the second case, we have two parts, one of size 5 and one of size 4 and one of size n minus 5. So the sizes of parts are very unbalanced. They are very different. Okay, so I claim that in this case, the running time is also going to be quadratic. And this can also be shown just by unwinding this recurrence relation. So let's just throw away this T of 4 and leave only T of n minus 5. And so T of n is equal to n plus T of n minus 5. Let's replace T of n minus 5 with n minus 5 plus T of n minus 10. Let's then replace T of n minus 10 with n minus 10 plus T of n minus 15 and so on. So this leaves us with the following sum, n plus n minus 5 plus n minus 10 and so on. And this is also an arithmetic progression. The only difference with the previous arithmetic progression is that now we have step 5. The difference between neighbors is 5, but not 1. Well, still, this arithmetic progression has a linear number of terms, which means that its sum grows quadratically, with the only difference that the hidden constant inside this theta is smaller than in the previous case. Now let's consider another pathological case. Assume that it somehow so happens, for some unknown reasons, that at each iteration, at each call to the partition procedure, it partitions the array into roughly equal sizes. Well, in this case, we can write the following recurrence relation on the running time of our algorithm. T of n is equal to T of n over 2 plus a linear term. And we know this recurrence already. It is exactly the recurrence that the running time of the merge sort algorithm satisfies, right? And we proved that in this case, T of n grows as n log n asymptotically. And let me remind you how we proved this. We analyzed the recursion tree of our algorithm. So in this tree, at the root, we have one array of size n. At the next level, we have two arrays of size n over 2. At the next level, we have four arrays of size n over 4, and so on. So the height of this tree is log base 2. Well, it is basically logarithmic. And at each level, the sum of the sizes of all arrays is equal to n. So we have one array of size n at the top, two arrays of size n over 2 at the next level, the sum is n. The four arrays of size n over 4 at the next level, the size is still n, and so on. And at each level, we spend a linear amount of work. And this is essential. So we spend a linear amount of work at each level, and we have a logarithmic number of levels, which means that we spend an n log n time in total. Okay, now let's consider another, again, very pathological case. Assume that we always split an array of size n into two parts, one of size n over 2, n over 10, I'm sorry, one of size 9n over 10. So in this case, the recurrence is the following. T of n is equal to T of n over 10 plus T of 9n over 10 plus a linear term. I claim that even in this case, we can prove an upper bound n log n on the running time of our algorithm. And this is how we can do this. Well, let's again consider the recursion tree of our algorithm. In this case, it is not balanced, right? Because when we go to the left branch, we reduce the size of the current subproblem by 10, and when we go to the right branch, we reduce the size of the current subproblem only by a factor of 10 divided by 9. Which means that in our tree, well, the size of the left branch is of the leftmost branch is actually log base 10 of n, while the size of the rightmost branch is log base 10 over 9 over n. Well, still the height of this tree is logarithmic. The only difference with the previous case is that now the base of the logarithm is different, but it's still constant. It is log base 10 over 9 of n. And also, but the previous property is true. I mean, the sum of the sizes of all arrays at each level is still equal to n. It is at most n, actually. At the root, we have one array of size n. At the next level, we have two arrays, one of size n over 10, and the other one is of size 9n over 10. Right? So the size is still n. At the next level, it is the same, and so on. So we have a logarithmic number of levels, and at each level, we spend a linear amount of work, which gives us an n log n upper bound once again. Okay, all this analysis was about only pathological cases. If we always split in a balanced way or in an unbalanced way. In reality, or just when we run a quicksort algorithm on some array, well, some of the partitions are going to be balanced, some of the partitions are going to be unbalanced. So we still do not know what is the actual running time of the quicksort algorithm. We still need to determine this. However, we already get an important message. So the running time of our algorithm, of the quicksort algorithm, depends on how balanced our partitions, right? What we know now is the following. If all our partitions are balanced, then we can prove that the running time is at most n log n, asymptotically. At the same time, if all our partitions are unbalanced, then the running time is quadratic. This means that we would like to have a way of selecting a pivot element such that it always guarantees a balanced partition. At the same time, it is not clear at all how to do this, how to guarantee that we can always pick quickly the pivot element so that with respect to this pivot, the array is partitioned in a balanced way. So instead of this, we will use the following elegant solution. So let's just select the pivot element from the current subarray randomly. To implement this solution, we do the following. Before calling the partition procedure, we just select a random index between L and M, and we swap elements A of L and this random element. Okay, then we call partition, and then we proceed in a usual way. Let me explain intuitively why selecting a random partition is going to help us to prove a good upper bound on the running time of the quicksort algorithm. Well, for this, consider our array A that we're going to partition with respect to a random pivot, and consider its sorted version. Assume for the moment that all the elements inside our array are different. In the sorted version, consider the middle half elements. Well, we consider n/2 elements that stay exactly in the middle. Well, an important property of all these elements is the following. For each of these n/2 elements, there are at least n/4 elements that are greater than them, and at least n/4 elements that are smaller. Well, this means that if we select any of these elements inside our array A, then the partition with respect to this element is going to be balanced. Right? In both parts, there will be at least n/4 elements. Well, these n/2 elements stay somewhere in the initial array. So they stay in the middle in the sorted array, and they stay somewhere in the initial array. It doesn't matter for us. What is important for us is that there are at least n/2 elements with respect to which the partition is going to be balanced, which means that with probability 1/2, we will have a balanced partition. And this happens to be enough to prove a good upper bound. So we're going to show that the randomized quicksort algorithm is actually very fast. Well, first of all, it is fast in practice, and also we will prove a theoretical n log n asymptotically upper bound on its running time. This is the formal statement of an upper bound on the running time of the quicksort algorithm that we're going to prove in the next video. So assume that we're given array A, and assume for the moment that all the elements of this array are pairwise different. Then the average running time of the quicksort algorithm on this array consisting of n elements is big O of n log n, while the worst case running time of this algorithm is n squared. Well, let me explain the word on average here. Well, this means that for any fixed array, so if we are very unlucky with the random bits, the running time potentially could be higher than n log n. However, on average, and averaging is over all possible random bits, the running time of the quicksort algorithm is n log n. And this is true for any input. So this theorem doesn't say us that, well, for quicksort algorithm, for some arrays the running time is large, for some arrays the running time is low, but on average the running time is good enough. So it says that for any fixed array, the average running time is n log n. Okay, so we are going to prove this theorem in the next video.